Okay, welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at the practice problems that we did as part of Chapter 17. Now, the first one we're going to look at goes back to ideas we talked about on day 2. Calculate the pH of a 0.500 liter of buffer solution composed of 0.50 molar formic acid and 0.70 molar sodium formate. So they're together forming a buffer, and those are the concentrations of each of those things. And then it says to also calculate the pH after adding 10.0 milliliters of HCl. So we're going to add a little bit of an acid afterwards. So we have two separate problems here. Now the first thing you should always do is take a look at the reaction that we're discussing. In this case we have the reaction between formic acid, so that's HCOOH, and that would normally be given in the problem, so don't worry if you haven't memorized what that is. We could just call it our generic HA, and that would work perfectly fine for what we're going to be doing the problem. So that's going to be thrown into water and form a hydrolysis reaction to form H3O plus and COOH minus. So that is the buffer system that we're looking at here. Now, in this particular case, we have this substance and we have this substance in the same container because it says we're 0.70 molar. So, oops, that's the sodium formate. Let me make sure I'm looking at the right numbers here. So up top it says 0.50 liters of a buffer solution composed of 0.50 molar formic acid. This is our formic acid, and that has a molarity of 0.50 molar. And sodium formate, which is going to give us the formate anion on a 1-to-1 stoichiometry. So this is 0.70 molar. So I have a buffer solution and I have a significant quantity of both a weak acid and its conjugate base. This is a buffer problem. So if we're going to do a buffer problem, remember we can use our plain old Ka equation, or we can use the Henderson-Hasselbalch equation, which is a little bit faster to spit out an answer. Now on top it's going to be our conjugate base, which in this case would be COOH minus. And on the bottom we're going to have our weak acid, which in this case is our formic acid, which is HCOOH. So really all we need to do at this point is plug in the numbers. Now the Ka, which is something that we'd have to go into Appendix D and look up. So if I look in Appendix D, it says formic acid is 1.8 times 10 to the negative fourth. So that's got to be something I get from Appendix D inside the book, or it'll be given the problem. In this case, it wasn't given, so I'm going to take the P of that, 1.8 times 10 to the negative fourth, and that's going to be added to the log of, remember, this is my base, so that goes on top here. And when I plug my numbers in the calculator and calculate, I get 3.89. 2 sig figs here, 2 decimal places as a p-value. So final answer is 3.89 is my pH. So that's my buffer system as it exists at the beginning. Now the thing is, when I add 10 milliliters of HCl, what's going to end up happening is I'm going to end up partially neutralizing this substance because this is a weak base, and when I add HCl, the HCl is going to give me H+, which will react with that, forming my weak acid. So I know this concentration is going to go down, and I know this concentration is going to go up because every particle of my substance, COOH minus, that disappears is going to become HCOOH. Now you got to remember, like in all neutralization situations, it's really how many moles do I have. So really, the very first thing I need to do is calculate the moles of the different things, because I've got concentrations here. And what I really need to know is my moles of COOH. So in order to do the second part of this problem, what we really need to do is calculate moles of all of the substances involved. So I need to know the moles of the COOH minus. I need to know the moles of the HCOOH. And I need to know the moles of my H plus that I'm going to be adding from my HCl. So those are really the three things I need to calculate here. Now remember, if I have a volume and I have a molarity, I can always calculate the number of moles. So that's always how you're going to be getting these. And that's why they gave me this, and that's why they gave me that 10.0 milliliters over there. So when I go to do my problem here, I have to pull out my information and do my calculations. So to calculate the moles of the formate, what I need to do there is take my 0.70 molar and multiply by the volume. Well, that was 0.500 liters. So when I multiply that out, I've got 0.35 moles of COOH minus. Now, in order to calculate the moles of my formic acid, I know it was 0.50 molar times the volume, which was still the 0.50 liters, because that's what I had in the original container. And that's going to give me 0.25 moles of my formic acid. Now, the last thing I really need to do is find my moles of the HCl, and that's the same calculation. I have a molarity of 1.00 molar times my volume in liters. So remember, I've got to take my 10 milliliters and change it into liters. Another sig fig there. So when I multiply that out, I get 0.0100 moles of HCl, which is also 1-to-1, going to give me, as a strong acid, that many moles of H+. Now remember, what's going to happen here is, as an acid, it's going to neutralize this substance. So the first thing I got to do to get my moles of COOH minus left is I have to take 0.35 and I have to subtract the 0.0100. And that's going to leave me with 0.34 moles of my COOH minus. Now, the other thing that's going to happen is the amount of my formic acid is going to go up by that number. So I have to take my 0.25 moles and I have to add my 0.0100 moles. And that's going to give me 0.26 moles of my formic acid. Now, at this point, I know my two concentrations, and I'm going to go right back to the same old equation. And really, the only thing that's going to change is my COOH, which is, remember my number up here, that used to be that number, and that used to be that number. And now what I've got is, now technically, I need to mention this before we move on, just in case I confuse somebody. We need to convert these back to concentrations to plug them into Henderson-Hasselbalch. But since they're new volume, after I add them together, it's going to be the 0.500 liters plus the 0.0100 amount. Once I add those two together, it's going to be the same total volume on top and bottom. So I'm going to take the shortcut here, and I'm just going to put on top my 0.34 and on bottom my 0.26. And I then do the math with that. So I'm going to take the log of that and add that to the P of 1.8 times 10 to the negative fourth. And now when I plug that in, I get 3.86 to 2 sig figs. So notice, after I added my acid and I neutralized some of my base and converted it into a weak acid, my pH dropped a little bit. A lot? No. Adding that much 1 molar hydrochloric acid, you would expect to see the concentration drop significantly. But because this is a buffer situation, it prevented it from changing a large degree in its pH. So really we saw a very small drop. Makes sense we were adding an acid that would drop. And it makes sense because it's a buffer system that it doesn't drop a ton. So that is how you do the day 2 calculation, dealing with buffer. Remember, Henderson-Hasselbalch is an easy way to do that, and that will be given on the Chapter 17 test. Now, the next situation, day 3, we get into strong acid, strong base titrations. So strong titrations, I'm going to call them. Now, one of the things that we talked about in class is there's really 3 things you should always know when you go into a strong titration, because they're going to be useful throughout the whole problem. 1, write the neutralization reaction. Never avoid that because it reminds you of the key stoichiometry. Now I'm going to use that stoichiometry to find the equivalence point volume, because that's going to help me figure out where I'm at, because there's 4 parts to a titration problem. Where I'm at, the math can be slightly different. So if I establish what my equivalence point is, it's going to help me answer questions. And the third thing I'd like to know going into one of these problems is to find the moles of, it's not necessarily an unknown, so I'm going to get rid of that. But when we originally talked about titration, what went in the flask was our unknown. In this case, it's whatever's going to be in the beaker or flask, not in the burette. So That's something that's never going to change. Yes, it's going to get partially neutralized and eventually totally neutralized as we go through the process of the titration, but how much is in there at the start never changes, and that's something I always want to know. So those are three things I can always figure out before I even worry about the problem. So I'm not going to worry about what it asks. I'm going to look at what it says. A 25 milliliter volume of 0.50 molar HNO3 is titrated with 0.25 molar KOH. So I have that strong acid inside a flask, and I'm going to be adding KOH to it. So the first thing I really want to do in one of these problems is I want to write the neutralization reaction that occurs. So I'm adding that strong acid to that strong base, and what it's going to do, single arrow here since it's not equilibrium, is I'm going to make HOH, which is just water, and I'm going to make KNO3. So that would be my reaction. Now, next thing I need to do is balance it. Well, it's a 1-to-1 to 1-to-1 stoichiometry. So that is my balanced neutralization reaction. And it reminds me of something very important. These two things mix at the equivalence point on a 1-to-1 ratio. And that's something I'm going to use in step 2, finding the equivalence point, which is exactly what they want me to do. So in finding this one, we're actually doing what the question asks. So if that is my balanced chemical equation for the neutralization, how does that help me find the volume at the equivalence point? Now remember, when you do any stoichiometry problems, are fundamentally 3 steps. So I've got my given at the beginning, I've got my target at the end, and stoichiometry is really about 3 things. Going from moles of one thing to another, which is typically done here, getting to moles, which is done here, and then getting out of moles, which is done there. So that's my typical problem. That's why I'm setting this thing up as 3 steps going in, because I know this is a stoichiometry problem. Titration is stoichiometry. Now, in the beginning, I have a volume of 25 milliliters, which I need to change to liters. So I've got 0.0250. Oops, too many significant digits. Let me get rid of that 0 there. So in the beginning, I have 0.025 liters of HNO3. And what I'm trying to get to is my volume of my KOH. So that's my question. Is at the equivalence point, how many KOH? So I know I've got 0.025 liters of HNO3, and I want to get to KOH. Now, remember the middle step. It's always going from moles of one thing to moles of another. So I want to go from my HNO3 to my KOH here. Now, remember, I get those numbers from the balanced chemical equation. That's why you always have to start with that, because this is an applied stoichiometry problem. So those are both going to be 1s in this case. Now, I've got liters of HNO3, which I don't want, so I know that's going to go on the bottom. And what I've just figured out here is I want moles of HNO3. So what conversion factor deals with moles and liters? Well, that looks suspiciously like molar or the molarity. Well, right here is my molarity. And remember, 0.50 molar HNO3 means 0.50 moles per every 1 liter. So I know I have 0.50 moles for every 1 liter. Now, on the back end of the problem here, my get out of moles situation, well, I don't want moles of KOH. The question was, what is the volume of KOH? Well, that looks suspiciously like what I just did over here. That's moles in liters. This is moles in liters. So this is going to be molarity. And there's my active molarity here. I have 0.25 moles of KOH for every 1 liter. So my math problem is literally now set up. Every unit cancels except the unit I want. So this must mean how I have to go about calculating this problem. So at this point, I just plug in and calculate. So 0.025 times 0.050. Let me grab my calculator so I can get this number. So 0.025 times 0.5. All the rest are 1s on top, so I'm not going to worry about them. Divided by 0.25. And at the equivalence point, it says 0.05 liters. Well, that's 2 sig figs. That's 50 milliliters. So in this particular problem, I'm going to end up with 50 milliliters being my equivalence point. So at the equivalence point here, I have a volume of 50 milliliters. Now, that's basically the first part. How do I calculate my volume at the equivalent point? Well, it's going to be 50 milliliters in this particular problem. Now, before we move on, up here, we're supposed to also find that, the moles that are in the beaker or the flask. Well, if you notice up above, that's exactly what I did right there. So the other thing that would be useful to know is how many moles of HNO3, which in this particular case is going to give me my H plus. So if I take 0.025 times 0.5, I should get 0.0125. So another useful thing to know at the beginning of this problem is I have 0.0125 moles of H plus. So I've now established my three things I should know at the beginning. I wrote my neutralization reaction. That helped me find my equivalence point volume. And I also found how many moles of that substance, HNO3, which gives me H plus, I've got inside my flask. And remember, that's always going to start with the exact same number in every single situation. Now, the next thing we're going to do is look at part B. Now in part B, it asked me to calculate the pH at different spots along the way. Now, I just found out my equivalence point volume is going to be 50.0. So, I know right away, at 50.0 milliliters, I'm at the equivalence point of a strong. Well, in a strong titration, at the equivalence point, my H plus and OH minus are equal to each other. That means that's got to be pH 7. I know that without any math whatsoever. So, if I want to know what my pH is going to be here to correct sig figs, which 2 sig figs, that should read 7.00 pH. So that would be my pH at my equivalence point. So remember, finding your pH or finding your equivalence point volume is really useful because it gave me the answer to one of the problems. Now it also reminds me then that this is before the equivalence point and this is after the equivalence point. Also two useful things to know. So going into my problem, I know that pH of that one is going to be 7.00. So I'm going to record that answer off here to the side. So I know pH here, 7.00. So for all intents and purposes, that one's done. Now, whenever you go to do a strong titration, what you really need to remember is it's all about how many moles of H plus and OH minus do we have. Because these things mix on a one-to-one stoichiometry, so it's really find those two things and subtract. Now, how do we find them? Remember, molarity times volume in liters always gives us the number of moles. So really in each of these problems, we need to start by finding these two things. Well, on the previous slide, we just found out that the moles of H plus is 0.0125. So I don't really need to do that calculation. For this particular set of numbers that I'm going to use, I know this is 0.0125 moles. And it's going to be that here, and it's going to be that here, and it's going to be that here, and it's going to be that here. My starting point for all of those is that number of moles of H plus. Now I also need to know how many moles of OH minus are coming together with that number of moles of H plus. Once again, I got to go to that top equation, molarity times my volume in liters. So basically I go through in each situation and I do that calculation. Now in the first one here, it's actually fairly simple. At 0 milliliters of NaOH, I haven't started my titration yet, so I don't have any of that stuff. But I do need to go through and calculate it for when I have 25 milliliters. So if I take my 0.025 milliliters and multiply it by the concentration of my KOH, which was 0.25, I get 0.00625 in this problem. And if I take it 0.050, this in liters, times my 0.25, I get 0.0125. Notice they're equal. We already established that. So this one's going to be nice and simple. We're already done. That one's over there because we're at the equivalence point. And then the last one, when I multiply 60 milliliters back to liters times the original concentration of 0.25, I'm going to get 0.015 moles. So those are my moles of OH minus in each case. And remember, these two things are coming together and neutralizing. Well, in the first problem here, there was nothing to neutralize. And just as a reminder, remember I had 25 milliliters of my HNO3. And I also had the volume that's given here of my KOH. Make that look like a K. So, why is that important? Well, after I neutralize my acid and my base, to get it to a concentration so I can calculate pH, I need to divide it by the total volume. And once again, that's got to be volume in liters, so I get molarity, moles per liter. So in this particular case, if that's how many moles I've got, and I'm not losing any of it, I've got 0.025 moles divided by my total number of liters. Well, 25 milliliters in liters is 0.025 liters. And when I divide those two things what I end up with is going to give me what my concentration is at that particular point. Now this one's actually even easier. Because I haven't added any of this, I can actually go back to my original concentration of my HNO3, which it said was 0.50 molar. So realistically, I know in this particular problem, before I've added any, since it's a strong acid, my HNO3 concentration is going to equal my H plus concentration, which was 0.50 molar, which is exactly what I'm going to get when I divide that. So remember, I got a couple of different ways. The easy way, this one, and the work way, that one. But in either case, I get the same molarity. All I need to do is take the negative log of 0.50, and that's going to give me my pH, which ends up for this one 0.30. So starting out very acidic. Now, the next one I actually have to do a neutralization here. I've got 0.0125 moles of my acid, and I'm mixing it with 0.00625 moles of my base. So when I subtract those two, I'm going to see how much of my acid I have left, which is 0.00625 moles left. Now remember, I have to take, so notice I actually neutralize exactly half of that. I have to take that to get back to a concentration. So I have 0.00625, and I need to divide that by my total volume in liters. Well, I had 25 milliliters mixed with 25 milliliters, so I now have 50. So in liters, that would be 0.050 liters. So I can't forget to divide those two things to get my concentration, and I'm just going to take the negative log of that, because that is my H plus concentration at this point, and I'm going to get 0.90 is my pH there. So I'm going to start at 0.3, and after adding 25 milliliters, I'm up to 0.9. After adding 50, I'm at 7.00 because that was my equivalence point, and I always know it's going to be equal. And now I have this final situation left after my equivalence point. Now I've got a whole bunch of OH minus. So now I'm going to take and subtract from my base my 0.0125 amount of moles to see how much of my OH minus I have left. And in this particular problem, when I do those subtractions, I'm going to get 0.0025 moles. Now remember, if I take that and convert it back into a volume by dividing it by my overall volume, so 60 plus 25, that's 85 milliliters. So I'm going to need to divide that by 0.085 liters. And remember, I'm taking the negative log of that quantity, and that's going to give me my pH. Well, hold on a second. Remember, this represents OH minus. So if I take the negative log of that, I have to subtract it from 14. So 14.00 minus all of that stuff is going to give me my pH, which ends up being 12.47. So be careful what you've got. In this case, I had H+. In this case, I had H+. In this case, they had neutralized each other. And in this case, I have OH minus. So you always have to find out how much is left and what you have left. Don't forget that important step. So those are your pHs. Now, the last thing to do is to draw a titration curve for this. Now, you'll notice I've already plotted out those points that I just discovered. And all I really need to do is fill it in. Now, I'm going to know it's a strong, so I'm going to get a big swing here right around my pH of 7. And all I really need to do is fill that out. So that's a rough idea of what my pH curve would look like for this problem. Next one, a little bit more challenging. Now, it's going to start with the same idea. We've got to know those three things, but it would also be useful if I knew my Ka and my Kb for this problem. So when I go to do this, I really need to have the same kinds of things that I knew before. Plus, since it's a weak strong situation in day 4, I'm also going to be doing some equilibrium math, so that would be my Ka and my Kb. And remember, I get the Ka value from Appendix D. So the number I'm going to pull out, that's where I got it from my book. But to start, I'm going to look at the same thing. I need to write my neutralization reaction. So I have acetic acid, which it says is CH3COOH. That's going to be added to NaOH. So these two things are neutralizing each other. And fundamentally what's happening is I'm pulling in hydrogen, this hydrogen, that's my ionizable hydrogen here. And I'm going to be putting that with OH minus from over here, and that's going to give me my water. And I'm also going to get sodium acetate, which would be NaCH3 COO. So that would be my neutralization reaction. When I balance it, it's a 1 to 1 to 1 to 1, which is something I need to find out this thing. So that's done. Next, find my equivalence point volume. Well, I need my balanced equation to do that. I've got it. It's a 1-to-1 stoichiometry. So this is going to be looking like just what we did on the previous problem. So we start with our known information. So we have 35 milliliters of acetic acid. Well, that's 0.035 liters of acetic acid. Stoichiometry means 3 steps. So I'm going to do a 3-step problem here, and that will give me my liters of my NaOH at the equivalence point. So that's the first thing I'm going to do here. Now, I know here's going to be my go to moles of one thing to moles of another, and that would be from my acetic acid to my NaOH. And I know from the balanced equation it's a 1-to-1 stoichiometry. And I want to go from liters to moles. That looks like molarity. Remember my substance here is still acetic acid. And molarity, since I look at the problem and I see it's 0.10 molar, that means I have 0.150 moles for every 1 liter. And then at the end, well, I'm in moles of NaOH and I don't want those. What I really want would be liters of NaOH. And once again, that's moles and liters. That's molarity as a conversion factor. But now I'm using this molarity. Oh, it turns out to be the same. So it's 0.150 moles per 1 liter. Next thing to do would be to plug my numbers in and do my calculation. And I end up with 0.0350 liters, which is another way of saying I've got 35.0 milliliters. That's my equivalence point. Now, what's the volume of the half equivalence point? Well, the half equivalence point, I'm halfway to the equivalence point. So half of 35.0, well, that's going to be a pretty straightforward calculation, 17.5 milliliters. Now, what's the pH at the half equivalence point? Well, the special thing about the half equivalence point is that your pH equals your pKa. So here's where knowing Ka of my acid would be really useful. Well, if I look up in Appendix D under acetic acid, I find out that the Ka of acetic acid is 1.8 times 10 to the negative. Make sure I'm copying down the right number here. So Ka of acetic acid, 1.8 times 10 to the negative fifth. And that would mean my Kb of my acetate anion. So while I'm finding my Ka, let's also look at what my Kb is. So later, if I need it, I've got it. Well, if I take 1 times 10 to the negative 14 in my calculator, and I divide it by my Ka, 1.8 times 10 to the negative fifth, I get my Kb of the conjugate. So that's my Ka, 1.8 times 10 to the negative fifth. Well, the Kb of the conjugate of acetic acid, the acetate anion, which is something I'm going to eventually need anyway, would be 5.555, and that just keeps repeating, times 10 to the negative 10th. So those are my two useful Ka values, which are always nice to know at the beginning, because case in point, when we get to see here, I need to take the negative log of my Ka. So I would take in my calculator, literally, the negative log of 1.8 times 10 to the negative fifth, and that would give me the pH at the equivalence point, which ends up being the 2 sig figs, 4.74. So I've got a weak acid, so it makes sense it should be less than 7, and it's a weak acid, so it's not a lot less than 7. So that seems to make sense. So that would be what is known as the half equivalence point. The half equivalence point in a weak strong titration is when your pH equals your pKa. Always a useful thing to know. Now, after this, we're going to get into our problem, but we never did find this right here. So one of the things I said you should find, and that's number 3 up here, is the moles of what's in the beaker or in the flask. Well, that would be 0.035 times 0.150. So that much of that stoichiometry problem is exactly what I need in order to find my moles of what's in the flask, which in this case would be my acetic acid. So my CH3COOH moles end up equaling, when I do this math up here, so that is going to equal 0.00525 moles, Remember, that's when my flask, that's always what starts out in my flask. So when I go to find my moles of each, that's always going to be my starting point here. So remember that number, 0.00525 moles. That's my acetic acid. Because one of the things I would like to establish in many of these problems is how much of that I have left. So let's remember CH3COOH in my beaker is 0.00525 moles. Now, how much of my base do I have? Well, I don't really know because that's going to be different for each and every problem. So I've got 0.00525 moles there. Now, calculate the pH each of the following situations. First one, 0 milliliters. Well, remember, we found out on the previous page, at the equivalence point, we have 17.5 milliliters. So, oops, sorry, I looked, that's the half equivalence point. The equivalence point was right here, 35.0 milliliters. So, when I look at this one, hey, I'm at the equivalence point here. That means this is before the equivalence point, and I would bet that means my step 4 is after the equivalence point. Yes, it is, 37 milliliters. So those are the general things I know going to this problem. I know at 35.0 milliliters I'm at the equivalence point, so step 3 would be at my equivalence point. Now step 1, I haven't actually done a titration at all. So this is really looking at my acid. Now, it was CH3COOH, and all I've done here in step 1, since I've added 0 amount of base, is looked at the hydrolysis of it. That's going to be a equilibrium reaction, and that's going to make H3O plus and the acetate anion, which would be CH3COO minus. So my Ka expression is going to equal H3O plus times the acetate anion all over my HA, which is, in this case, acetic acid, which is CH3COOH. That's my weak acid. Now, I know from the previous page that this has to equal my Ka, which was 1.8 times 10 to the negative fifth. Now, this is a typical icebox problem. As this dissociates, I'm going to get x of these and x of those, so that's going to equal x squared over my original concentration. So going back to the original problem, what was the concentration of my acetic acid? Well, that was 0.150 molar minus x, because that's going to go down by however much those went up by. Now, at this point, we do our typical neglect x. To avoid the quadratic equation and make the math easier, we're going to take the square root of 1.8 times 10 to the negative fifth times 0.15, and that will equal x. So for this particular problem, x is going to end up equaling, which remember, x is H3O plus. That's going to equal 0.00164 molar, but it's only got 2 sig figs, so I'm going to underline that. So that's my H3O plus. If I take the negative log of that, that's going to give me my pH. And in this particular problem, that's going to equal 2.78. So what's the answer to the first part here? Well, my pH, when I have added 0 amount, so I have not started my titration yet, I'm going to have 2.78 as my pH, which I've got an acid, so it would make sense that I'm going to end up with less than 7. And remember, all I did was our neglect x, solve for x in a Ka problem, took the negative log of that, and I found the pH. Now that brings us to part 2. Now part 2 is before the equivalence point. And in a weak strong titration, that means we are forming a buffer. So what we really need to find is how much of that do we have and how much of that do we have, and we can plug it into the Henderson-Hasselbalch equation. So what I really need to do is take a look at what I've got. Well, I know I have 0.00525 moles of my acid, and that was CH3COOH. And to that, I was mixing 20.0 milliliters of my 0.150 molar NaOH. So if I take 0.15 and I multiply it by 20 milliliters in liters, I'm going to find out how much of my NaOH, which would give me my OH minus, because remember this is giving me my H3O plus, So the actual amount would be the 0.02 times the 0.15, and I get 0.00300 moles of my base. So it's NaOH, but I'm just going to write it as OH minus here. So that is how much acid, that is how much base I have. Now notice, this is a larger value. So when I subtract these two, I'm going to see how much of my acid I have left. And after subtraction, I get 0.00225 moles. Now, that's how much acid I have. But you need to understand that all of the acid I lost by my balanced equation up here became this. So this got converted to that. Now I had 0.00300 moles going down or losing. So that means my concentration of the CH3OO minus is also going to equal the 0.0030 molar. Now, the reason why that's important is in Henderson-Hasselbalch, the pH is going to equal the pKa, which remember that was the P of 1.8 times 10 to the negative fifth, plus the log of the base, which is my number right here. I might as well write it in up here. And now technically I'm supposed to divide these by the volume to get the concentration, but remember the volume is the same in both cases. So I'm going to put my base up here, and my acid, well, I had that many moles left, so on the bottom I'm going to put 0.00225, and I take the log of that, and then I'm going to plug that all in. So my pKa is the P of 1.8 times 10 to the negative fifth, and when I actually solve for pH in this problem and do the math, so remember that went right there, I'm going to get in this point a pH of 4.87. So yes, I've added a base, and yes, I have gotten more basic, but that would be how basic I am, or I should say how acidic I am at that point. So yes, my pH did go up, I became more basic, but now at 20 milliliters addition of my titrant, I'm at 4.87 as my pH. So what I've got here is a Henderson-Hasselbalch problem. So really, if I had a bunch of volumes before 35.0, I would do this. I would find out how much of this I neutralized, see what of this is left. That would go on the bottom, and however much I was neutralizing would go on top. Just plug them back in Henderson-Hasselbalch, and you can keep generating your pH values. So all those problems are going to look exactly the same. Now, the next one here was part 3, and that was where I was at 35.0 milliliters, which remember, that was where HA and our OH minus perfectly neutralized. So my acetic acid, my sodium hydroxide, exact number of moles of each. So I'm going to have 0 of those left, and that means all 0.00525 moles of my acid became my conjugate base. So that's how many moles I've got. Now, at this point, I'm going to be putting that in water. So remember, I need to look at what my reaction is. So I've got CH3OO minus is being put in water because that's all I've got as my conjugate base. Well, that's going to act like a base in an equilibrium reaction. And as a substance that acts like a base, it's going to steal hydrogen. So I'm going to get CH3COOH back to my acetic acid. And I'm going to get OH minus. So this is a Kb problem. So to solve this one, I would do Kb is going to equal CH3COOH concentration times OH minus concentration all over my CH3COO minus, my acetate. And I know that's got to equal Kb. Well, remember, back on the previous page, I said it was going to be useful, so we might as well find it. There's my Kb of the conjugate. It's 5.556 times 10 to the negative 10th. So, in this particular problem, that's going to equal 5.556 times 10 to the negative 10th. Let me double check. Yes, it is. And that's going to equal x squared over this back as a concentration. Now, I got to be careful here. That's how many moles I've got. And to get that to a concentration, I need to divide it by my total liters. Now, I just added 35 milliliters of my base. And remember, back at the beginning, I had 35 milliliters of my acid. So I need to divide that by 70 milliliters as liters. So 0.070 liters. And that will give me my concentration, which is going to go on the bottom here. So that is the concentration of that thing. So after I do my division here, I'm going to get 0.0750 molar. Be careful of that. This is the one that people make a mistake. They put 0.00525 down at the bottom here instead of 0.0750. And then we're going to neglect x, just like we do before, solve for x, and in this particular case, x is going to end up equaling, remember OH minus, because this is a KV problem, and it ends up equaling 6.5 times 10 to the negative 6th molar. Now, I can take the negative log of that and subtract from 14, and I get my pH, which is going to end up equaling, pH is 8.81. So notice at my equivalence point, my pH is not 7 like in a strong, because it was a weak acid strong base titration. I would expect it to be basic at the equivalence point because all of my acid, my weak acid is gone, but it's been converted into its conjugate base. So I should have a basic solution here. And that leaves the last one. So let me get a little bit more room here to work. Now I've got 37.0 milliliters added. Now I know I'm past the equivalence point here, and that's the same as a strong situation. Since I have OH minus extra, so I have a whole bunch of OH minus here. And remember, how much do I have? Well, I would take 0.037 liters and multiply it times my concentration of my base. And remember, the base was 0.150 molar. And that would tell me how many total moles I have, which is going to end up equaling 0.00555 moles of OH minus. Now remember, because it never changed, I have this much that I have to subtract from that. So 0.00525 is how much acid I've had in the flask the whole time. So when I subtract those two, it's going to tell me how much OH minus I have left. And when I subtract, I get 0.00030 moles. Now be careful here. This is the moles of OH minus. In order to find pH, I need two things. One, I need H plus, supposedly. And two, I need a concentration. So I need to get what that is. So take the moles of OH left, just found that, and divide it by the total volume. So I had 37 milliliters, and I added that to 35 milliliters, so I now have a total of 72 milliliters. So it's 0.0720 liters. That is going to give me my concentration of my OH minus. So remember, OH minus is going to equal the math here. And that ends up equaling 0.0042 molar OH minus. Take the negative log of that, subtract from 14, and I get my pH, which is 11.62 to 2 sig figs. So that will be my pH after the equivalence point when I've added 37.0 milliliters. So I've got fundamentally 4 different types of math problems here. Each one I want to find the same thing, the pH. Each one, it's a different type of problem. And that brings us to the last part, drawing the titration curve. Once again, I've already got my dots drawn in here. Now, the big difference between this is I know my big swing is going to be above 7 pH, and it is. So what we're going to have here is basically this kind of titration curve. So my big swing is not at 7, it's above 7 in this problem. So that would be an example of what the titration curve looks like. And that the final question from the chapter 17 practice problems, which is what we looked at in day 5, says what is the molar solubility of MgOH2 when buffered to a pH of 6.00? And the KSP of this is 1.8 times 10 to the negative 11th. So low KSP, low solubility. Now, if we dump magnesium hydroxide in water, the equilibrium reaction is the one I've listed here. It breaks apart into Mg2 plus and 2OH minus. Now, if we were just throwing magnesium hydroxide in water, we knew the KSP, we could use that to calculate the equilibrium concentrations. We could use that to calculate the molar solubility. And then we could use that if we wanted to calculate the solubility in grams per liters. But the thing is, you'll notice it said when buffered to a pH of 6.00. Well, what that fundamentally means is we've changed the pH. We've messed with the pH in this problem. And since OH minus is one of our products, if we increase or decrease the OH minus, it's going to change the solubility of the MgOH2. So at a pH of 6.00, how we go about calculating what the new molar solubility is to see if we increased or decreased. Because remember, if we shift to the right, we're increasing the solubility of magnesium hydroxide. If we shift to the left, we're decreasing it. So the first thing we need to do is recognize that this would be our KSP expression for that reaction, equal the concentration of Mg2 plus times the concentration of OH minus squared, and that's going to equal 1.8 times 10 to the negative 11th. Now, since we've messed with the OH concentration, we can't just plug in X and 2X and calculate X. We have to do this a little bit differently here. So what we have to do is recognize the fact that they tell us the pH is 6.00. Well, that means the pOH is 8.00, and some simple log math in your head, the negative log of, or I should say the antilog of negative 8 is going to give us a OH minus concentration of 1.0 times 10 to the negative 8th. So that is our OH minus. Well, we know by the KSP expression, Mg2 plus times OH squared has to equal 1.8 times 10 to the negative 11th. Well, since I know what my OH minus is, I can plug that into that equation, and I can solve for the Mg2 plus concentration. Now, what you need to realize is when we're solving for Mg2 plus, based upon the situation, the molar solubility of MgOH2 and Mg2 plus are going to be the exact same. So when I'm calculating for my new concentration of Mg2 plus, that's going to be related to my molar solubility of MgOH2 on a one-to-one basis. So if Mg2 plus ends up equaling 180,000 molarity, then that would be the molar solubility of MgOH2 as well. Well, that's an incredibly high solubility. Now, to answer the question, how does that compare to the normal solubility, which wasn't asked, but I want to make sure you understand how we would look at that. Well, what we need to do to answer that question is understand that we have to go back to the original equation here. Now, in this original equation, and let me get a little bit more room here. Extend the page down. In the original equation here, we've got MgOH2 dissolving in water to make Mg2 plus and 2OH minus. Now, if we create this by dumping solid MgOH2 into water, the stoichiometry is going to uphold. For every one of these, I would have to get one of those and two of those. So for every X of these that dissolved, I would get X of these and 2X of those. So based upon my original KSP expression, which remember was Mg2 plus concentration times OH minus squared, if Mg2 plus was X and OH minus was 2X, and that quantity would have to be squared, the KSP would then equal 4X cubed. So if we solve for X, so we divide our original KSP, which would go back up at the top here. So we're taking that. So up at the top here, we're taking that, and we're dividing it by 4, and then taking the cube root of it, we would actually calculate what X is. And remember, X is going to equal the saturated concentration of Mg2 plus, which would equal the molar solubility of MgOH2. And what X ends up equaling here is 1.7 times 10 to the negative 4th molar. So fundamentally what happened when we adjusted the pH is we went from a molar solubility of 1.7 times 10 to the negative 4th, which is very small, to a molar solubility of 180,000. So adjusting the pH dramatically increased the solubility of MgOH2.